In previous videos, we learned how to use the chi-square goodness of fit test when we have a single categorical variable that reflects different groups in the population. We used it to test whether the distribution of cases across the population equaled specific values that we expected to see for each of those groups, assuming the null hypothesis is true. In this video, we're going to learn a second, different chi-square test called the chi-square test of independence. While we used the goodness of fit test when we had a single categorical variable, we use the test of independence when we have two categorical variables. And as the name suggests, we use it to determine whether those two variables are independent of each other. Now, before starting, let's take a closer look at what we mean by two variables being independent. In this context, we're not talking about independent variables that we described when we covered independent and dependent variables. This is a different use of that term that's more aligned with the concept of independent events in probability theory. In this context, two variables are independent if the occurrence or level of one variable does not influence the probability or the occurrence or level of the other variable. Because we're dealing with categorical variables, we can think of this more precisely as whichever group you're in for one variable doesn't change the likelihood of whichever group you're in for the other variable. For clarity, let's consider a hypothetical example and say that I've sampled 450 people from Maine, New Hampshire, and Vermont and asked them whether or not they've ever visited Disney World. So we have two categorical variables. One, what state you live in, which has three different categories, Maine, New Hampshire, and Vermont. And the second, have you visited Disney, which has two different categories, you visited or not visited. To start, let's see what the data may look like if the state you live in and whether you visited Disney are independent. All right? So here's an example of data where state and Disney status are independent. Notice we've organized it so that we have two rows indicating whether someone visited Disney or did not visit Disney. And we have three columns indicating the state in which someone lives. That gives us 6 cells or 6 boxes that reflect the 6 different combinations that someone may have for these two variables, with the number in each cell indicating how many people had that specific combination of state where they lived and their Disney status. For example, 45 people lived in New Hampshire and visited Disney. All right? Now, for clarity, at the end of each row, we also indicate how many total people there are in each of the Disney groups. So we see 135 have visited Disney and 315 have not. And at the bottom of each column, we indicate how many total people there were in each state. So we have 200 from Maine, 150 from New Hampshire, and 100 from Vermont. We also indicate the overall total of 450 participants in our study, right? Now, why are these two variables independent? Well, if we look at the overall percentage of people who went to Disney, That would be 135 out of 450, right? That works out to 30% of our total sample have visited Disney. Now, knowing that, let's change these numbers to the percentage of people in each state who visited Disney. All right, here we are. Now, notice something here. Within each state, the percentages are exactly the same. 30% have visited Disney and 70% have not. Whichever group you're in for state has no effect at all on the probability that you visited Disney. It's always 0.3 or 30% of the sample from that state, for every state. Now, notice that the ends don't have to be equal. We have more people from Maine than New Hampshire and more people from New Hampshire than Vermont. And also notice that the percentages don't have to be equal either, right? If we look, it's not 50-50, is it? It's 30-70. Again, to be independent, whichever group you're in for one variable, in this case the state you live in, has no impact on the probability of the other variable. In this case, it has no impact on the probability that you visited Disney. Now, another way of thinking about this is that knowing something about one variable tells you nothing about the other variable. Knowing which state you're from tells you nothing about whether you visited Disney. It's always 0.3 or 30%, regardless of the state you live in. Now, what about looking at this based on whether or not someone has visited Disney? Of the people who have or have not visited Disney, what's the percentage from Maine, New Hampshire, or Vermont? In other words, let's look at the percentages across each row instead of down each column. All right? So here are those percentages. Notice it's the same pattern. Within both the Disney and no Disney group, the percentage of people from each state are exactly the same. 44% from Maine, 33% from New Hampshire, and 22% from Vermont. Whichever Disney group you're in has no effect on the probability that you're from any of the states. Okay? Now, let's change these numbers slightly so that the two variables are not independent. We'll keep the ends for each state the same, but have many more Mainers visit Disney and fewer people from Vermont do so. Now, at this time, now let's take a look at the percentage within each state who visited Disney. Among Mainers, 75% have visited Disney, while among those from Vermont, only 10% have. The group you're in for the state variable does influence the probability that you visited Disney. They're no longer the same. They're not independent. In this case, knowing something about one variable, which state you're in, does tell you something about the other variable, whether or not you have visited Disney. If I know you're from Maine, I know you've probably visited Disney. On the other hand, if I know you're from Vermont, I know that you probably haven't. Okay? So that's what we mean by two variables being independent. So returning to our chi-square test of independence, the purpose is to examine whether a person's value on one categorical variable is independent or unrelated to their value on a second categorical variable. And like all statistical tests, we do have some assumptions, right? First, we need to be examining two categorical variables. Now, these could have been continuous variables, such as standardized scores of a reading assessment that were transformed into categories such as advanced, proficient, partially proficient, or not proficient. But they need to be categories for this analysis. Second, the observations need to be independent. There's that word again. I mean, I swear, we really need a larger vocabulary. In this instance, we're talking about observations being independent. That just means that whichever categories one person is in is unrelated to whatever categories another person is in. Returning to our example earlier, if Keith lives in Maine and has visited Disney, that has no impact on which state Lori lives in or whether Lori visited Disney. All right? Also, the categorical variables need to be mutually exclusive. A person must be in one and only one group for both of the variables. And finally, remember that 2x3 set of boxes we created when we looked at the Disney status and state in which someone lived? As a general rule, you typically want at least 80% of the cells to have at least 5 expected cases and none of the cells to have fewer than 1 expected case. All right? With that, this is a good point to end this video. In our next video, we'll start the process of walking through a chi-square test of independence, step by step, from hypotheses to our conclusion. All right? Can't wait. See you then. Bye-bye.